for part of the group ICESaT, and we are Team Ocean. I'm Skylar Radka.
I'm Sam Elvis.
I'm Hannah Gallimanis.
So some of the things we'll be going over is biography, so you'll get to know us a little bit better besides our names and our faces. And you'll learn what ICESaT is, some of the campaigns that went on with ICESaT, problem solving, planning, how we're going to tackle this situation, graphs and maps that we made, bias, reflection, and some acknowledgments.
So I'm Sam Elvis. I'm from right here in Austin, Texas. I attend the Liberal Arts and Sciences Academy, LASA. It shares a campus with LBJ, for those of you who are from town. And I'm going into 11th grade.
My name is Hannah Gallimanis. I'm in Beaverton, Oregon. I go to Arts and Communication Magnet Academy, and I'm going to be a senior.
Again, I'm Skylar Radka. I'm from Reading, Pennsylvania, Muhlenberg High School, and I will be a senior this year.
So the satellite we looked at was ICESaT, and as Margaret said, it stands for Ice Cloud Land Elevation Satellite. It's a NASA satellite that has an altitude of 600 kilometers and an inclination of 94 degrees. It has a near polar inclination, which allows it to still monitor the poles. However, it has 94, so it's not exactly polar, which allows it to have crossover tracks, which is really important for the data. The one instrument it has on board is GLASS, or the Geoscience Laser Altimeter System. It has two different wavelengths, infrared at 1064 nanometers and green at 512 nanometers. And it fires at 40 hertz. It was launched January 13, 2003, and it ended August 27, 2010. GLASS is the one system on it. It had 3 lasers that would fire. The original idea was to have lasers on for 91 days. This would allow it to cover the whole Earth. However, they turned on laser 1, started firing it January 20th, 2003, and it failed March 29th, 2003, so it only lasted 37 days. This made them adjust the campaign, so instead of 91 days, it would be 33 days. This allowed it to go over the whole Earth. It just didn't do the repeat tracks to fill it all in. These are all the campaigns that it ended up doing. Over the whole mission, it got about 2 billion laser altimeter measurements. For our research specifically, we're going to look at L2B, so the second time that the second campaign for laser 2. And then from that, it makes it more manageable to look at the data, and what we find can be applied to the other campaigns.
So what we are looking for in our data is we're trying to graph and compare sea surface anomaly and look for a way to reduce it as much as possible. So sea surface anomaly is basically, it's a difference between the sea level elevation that has been recorded by previous satellites, all averaged together, which is a pretty good estimate of what the sea level is globally. And it's the difference between that and the sea level elevation as recorded by ICESaT. Some of this, of course, can be attributed to seasonal changes, global warming, stuff like that, which is what ICESaT is trying to record. So we don't want to eliminate those variables, but we do want to eliminate as many other variables as possible to get as accurate of a picture for those as we can. So we're going to be comparing sea surface anomaly with transmit pulse major axis, which is the diameter of the footprint of the laser, because, fun fact, lasers aren't that laser-like when they're from 600 kilometers up. And so it gets spread out fairly far. And so I believe the aimed side was 70 meters. Some of them were, actually I believe most of them were a lot wider than that, a lot less accurate. But that can affect the sea surface anomaly. Gain value for return, which is basically the sensitivity of the receiving equipment, that can also affect sea surface anomaly. It's measured in counts, by the way, which is just the level that they set it at, basically. Then received energy, which is the amount of energy the satellite records when receiving. That's measured in joules, very small amount, but of course it's just they're trying to measure the amount of energy that comes back at them when they fire the laser. And that can also get a lot of interference and stuff like that, so that one starts getting particularly hard to manage. So there's sea surface anomaly with that, and it's very closely tied to reflectivity, which is how reflective the surface is, of course. And so that also has to do with sea surface anomaly.
So the plan of action is we have to sort through campaign L2B text files, which are basically Notepad program, and it has well over 2 million numbers in it. So you can't really open it. So you have to use a special program to figure a way to open the actual file, and you have to extract the needed variables. Because in the notepad, the numbers are broken into several columns, and you have to choose the columns that you want depending on what kind of graph you want to make. And we would use these variables and plug them into code, and we would be able to make graphs and maps and point out clear trends of sea surface anomaly. And again, we would map these, and we would use variables against each other, and you'll see that later. And we would report the findings, which is what we're doing right now.
Most important step.
And this is an example code of what we used. We were using GMT, and just simple things I can point out that would make it a little easy to read is we would be using a little graph here, we would name it here, and we can determine if it's going to be a portrait or a landscape, and that's up top here.
Yeah, and then the body of the code down here is just several different instructions with tons of different parameters. They get complicated, some of them are redundant. We didn't even get into most of them, but we adjust some of the basic parameters like size, how specific we want the scale to be, and we end up producing graphs.
So the very first thing we wanted to do is graph sea surface anomaly by all the different variables we were testing. So the very first thing we did was sea surface anomaly by the transmit pulse major axis, and that's the graph over there. So we saw that the majority of the data was bunched in the middle, but we really want it at 0. That was our goal. So what we wanted to do is random average it to see if it was actually at 0, and we got this graph over here. And as you can see, it's slightly off 0. So that showed us that when comparing transmit pulse and major axis to sea surface anomaly was negative, less than what we thought it would be. So by fixing that and bringing it closer to 0, that would be one way to help the overall sea surface anomaly. Next thing we did was sea surface anomaly by gain value for return, and we got a really similar graph to the one we got before. So we have a bunch of data clumped in the middle, and we couldn't really tell if it was on 0 or not. So we did the random averaging again and got this graph over here. And it's really hard to see, but 0 is right here, so you can see that most of the data is to the left of 0. Showing that the relationship between the gain value for return and sea surface anomaly is less than what we would think, so it's off 0. So correcting that would also be another way to help sea surface anomaly get closer to 0. And then the graph started getting really interesting. So this is what we really wanted. Sea surface anomaly by received energy. You can see down here where received energy is really low, sea surface anomaly is all over the place. Right here it seemed to be bunched around 0, but we'd have to average it again to see if that's actually there. And then we got this curve here, and that's how I knew that there was a bias there that we needed to correct. So one way to help sea surface anomaly be closer to 0 would be to shift this back up to 0 and make that help the sea surface anomaly be closer to 0. We wanted to come back here though and see if that was actually at 0, so we randomly averaged it again. We got this and saw that it was also shifted negative from what we wanted. So that's another thing we'd have to correct. And then lastly, we did sea surface anomaly by reflectivity. The -1 right down here is the error message the satellite gives if it can't record reflectivity. So, but the rest of it has extremely similar trends to the graph before. Really random down here, bunched around 0 again, and then we have that curve again. We want to bring it back up to 0 to fix sea surface anomaly. And then we wanted to see if that bunch was actually around 0 again, so we did what we've been doing before and randomly averaged the data, and we got this over here. And we noticed two things really quickly. The data averaged from 0 to 1.25, where we noticed the majority of our data was up there. And we also got data that was below 0 reflectivity, which doesn't happen. So we realized that it was actually calculated in the -1 error message and bringing the data down. But from this, we could still see that it was shifted again negative. So we need to bring that back up.
Good learning.
Now, one of the coolest things about coding is that you're able to customize your graphs, or you can make maps. And these two are maps. And if you look closely, you can see on this data line that you can see it goes from -1 to 1, and you have this map. However, you can make the numbers smaller, and you can get a much smoother map, and you can bring out more colors in the map, which I think is pretty cool. However, there's something much cooler than that. If you look, this is all satellite data. If you look at the Suez Canal, you'll notice that it's in the red area. That area is usually filled with ships because that is a major trading route. And I think it's really neat that the satellites are able to pick that up and we can graph it there.
So now we get into some colorful graphs. Basically what we did on these is we'd already plotted sea surface anomaly against the variables, and now I wanted to see if there were any sort of trends between the variables that we plotted. And so what we did here is we overlaid, we basically plotted gain value for return against transmit pulse major axis. And if you were to take the colors away from this graph, it wouldn't really tell you much. But what we did is we basically, instead of using a random averaging algorithm, we basically took each little grid square. You can see that these are composed of individual groupings of pixels. Each of those takes all the data that's in there and averages them out to a single sea surface anomaly. And so we used that to get a more comprehensive picture of an average. It may not narrow the data down for us and tell us where the data is centered on, but it will provide us with a nice image of the sea surface anomaly in relation to it. And so the first graph we made was this one on the left. Let's see if I can get this to work. So this graph over here, and you can see actually there are several little bands of slightly bluer regions, a band of slightly greener area, and then bluer area. And if you look at down here at the graph, that actually corresponds to changes in sea surface anomaly. And so we started seeing these sort of patterns, and we actually increased the contrast of the graph by shortening the range of colors. And we ended up seeing very clear bands where there were these areas of low sea surface anomaly, areas of low sea surface anomaly up here, and then this one band of higher than average sea surface anomaly. And so that was one thing that we figured we could fix as well, this sort of wavy pattern in the transmit pulse major axis when compared to gain value for return. Additionally, actually, there is a large area over here you can see where the sea surface anomaly is above average as well, and it tends to be lower over here. So there's also a slight trend in the entire graph. Then here we have received energy by gain value for return, the sea surface anomaly. So all of that is just overlaid with sea surface anomaly. And in a lot of these graphs, we started getting random data. So all this colorful stuff over here, it's not so much that the data is error messages or outliers, but just that because we started making the scale, because we started making the scale so specific, the data that was farther away from the center of the scale started becoming more and more outliers when we tried to focus it down to a really narrow average. Anyway, so if you ignore the outliers, you can still see a couple patterns here, especially right here. You can see that all the data points on the minimum count, the minimum gain value for return, they tended to be really low in sea surface anomaly, especially over the energy of 4e to the negative 14th joules. And so that's one thing we can note about this. And we tried to pull more and more data out of it too. First, we made the graph have more contrast here. And then we actually increased the resolution of the graph to see if we could draw anything from it. And when that didn't work, we just changed the graph. So we basically focused ourselves on one single area of the graph, the leftmost part of the graph, with energies between 0 and 2e to the negative 14th joules. Sorry, the scale for that is clustered. And you can actually see here that there is a clear trend where there's a positive sea surface anomaly here at the bottom. Then as you go to the left, it gradually increases to a negative sea surface anomaly, especially in the higher gain value for return count areas. And a similar thing showed up when we measured reflectivity, which makes sense because reflectivity is derived from the return energy. And so again, we have the negative data. I don't know if you can see that laser point. Negative data, thank you. Yeah, the negative data over on the lower count areas. And then you can also see here, we didn't bother to focus in on this one, but you can see some of the higher sea surface anomalies fading down to lower sea surface anomalies.
So the first set of biases we found were from the first graphs. We found the transmit pulse major axis. Sea surface anomaly is slightly below expected. With the gain value for return, sea surface anomaly is slightly below expected, especially around 130 counts. Third thing we found is that for received energy, as received energy increase, sea surface anomaly decreases rapidly. That starts around 1.5 e negative 14 joules, and sea surface anomaly continues to decrease as the energy increases. And the last one we found from the first graphs was for reflectivity. As reflectivity energy increases, sea surface anomaly decreases rapidly. This starts at 0.75 reflectivity, and sea surface anomaly continues to decrease as reflectivity increases.
So then, additionally, we found that the gain value for return by the transmit pulse major axis, that was the one where the data ended up making those slight ripples. And so, of course, we noted that. And we also noted the trend towards positive sea surface anomaly as you decrease the sensitivity of the instrument that counts for the gain value for return. Then for reflectivity and received energy, which were both similar graphs, we noted that the measurements with the low gain value for return and reflectivity above 1 or energy above 2e to the negative 14th, they all have negative sea surface anomalies when averaged. And we also noticed the slight trend of sea surface anomaly from positive to negative as the gain value for return was lowered, or increased, sorry. Maybe? It's not going to die on me. Okay, so we all got a little upset at the computers. It's hard not to when you're coding. For me, it was particularly dependence on the Falcon computer, which we were using to store and process a lot of our data. Additionally, you had to log in with ID every single time, and we had to, it kept prompting us for IDs, and it got kind of annoying. And then just the code in general was a kind of user-unfriendly interface, I guess you'd say. It was basically just using the command prompt and shell script, which are both low-level, shell script is a low-level programming language. And then that last one is just because I don't know how to code. But
So my hardest thing was learning to code. This is the first time I ever coded. So when I opened the GMT system we were using and it was a command prompt, I was like, okay, so I learned how to code now. Man pages was one of the most helpful things. It's just like, I think it's about 200 pages and it's just all GMT code. So that was really helpful. The hardest part with actual coding though was spelling. Code doesn't like if you mess up anything, especially spelling and grammar. My hardest thing was spaces. So I would either add a space or there wouldn't be a space, and then going through and looking for all the spaces I was missing, I'd spent a lot of time doing that.
I agree with Hannah with the spelling, because even if you do simple spelling errors and you accidentally miss the backspace button, you have to later on play I Spy and find the missing letter or the error that you have, because if you don't, you can't get anything out of it. And it's just that one letter that messes everything up. So that was a little tedious and did make me want to do that, but not to that extreme.
we avoided destroying any computers.
Yeah, all your computers are good. So also we had to log in every time. We had to get in connection with Falcon, which was the big computer that had all of the satellite data. And the struggles of coding in general, so basic spelling errors and also just a lot of repetition. And memorizing file names was a problem for me specifically, because I kept on messing up, and I would decide to make a new file and forgetting to delete the old file, so then I didn't know what I was messing with, and then I had all these files in my profile that I never used because those were scrap, and I ran out of names, so I had to get creative, I guess you can say.
Actually, I will say I tried the alternative. I would just save over the same file repeatedly, but that has the opposite problem where when you go back looking for data you've created previously, if you haven't saved it, it's already been saved over by the program, so it's really kind of hard to work around that one. So this is our personal reflections here. The NASA SEAS internship program means a lot to me. Just being selected, especially out of the 30, I believe it was, people, is incredible. And having the opportunity to work with real satellite data, using actual programming algorithms that CSR uses, it was a lot of fun. Some of the code was frustrating, of course, And it did end up postponing our project, but once we got to understand how GMT, the generic mapping tools system, worked, you could actually crank out several graphs each day. And it was exciting, though really annoying, to adjust the parameters of the code, but it was cool to see how you could manipulate the graph, extract certain data. That sort of thing was really interesting. This program taught a lot of skills: coding, team building, how to build pipe cleaner towers with one hand behind your back, though we did not figure that one out. Our tower flopped, literally. And then all these skills help prepare for a career in STEM, which is good because that's what I intend to go into. And it gave me real life experience working with these sorts of programs. And then also for the program in general, the combination of lectures, activities, individual work, and free time was perfectly balanced. It was a lot of fun, and I'm going to miss it.
So this may be the coolest thing I've ever done in my whole life. I had the opportunity to work with actual satellite data. I got to work with students who share common interests. I got to work with scientists who are extremely knowledgeable about their field and like what they're doing. I got the first-hand experience in a research environment, and that was, I think, the most important thing for me. Because I go to an art school and I study film, and then I tell my high school counselors I want to go into a STEM career, and they're like, yeah, okay, you do that, have fun.
Well, here you are. So.
I kind of made it a priority for myself to prove them wrong a little bit. After I got the internship, though, I started getting a little nervous. I realized the past 3 years of my life have mostly been dedicated to film, and the way I tried to make it manageable to come here and really see what an actual job in STEM would be like was to try to make the comparisons between film and STEM. One of my favorite ones that I made was being flexible towards a specific goal. So in film, when you're editing, you may have a shot that you 100% thought would work, and you put it in and it doesn't tell the story right. Similarly, there may be shots that you thought would never work, and you put it in and it tells the story perfectly. When we were doing our research, there was some stuff that we thought would answer the question 100%, and it would actually have no correlation. And on the same side, stuff that we never thought it would have worked answered the question a lot. So being flexible about how you're doing the process with film, how you're telling the story, and with this, how you're answering the question, but still telling the story or answering the question. So this comparison, along with many others I've made, has actually given me the confidence I need now to go pursue a career in STEM, which I'm really excited about.
And my personal intake about this program is I really thought it was an amazing first-hand experience, being able to sit down and figure out how to make maps and images, and the excellent opportunity to make new friends and the social network that we have in this building. Well, some of you guys like me, I don't know. But I will definitely recommend anybody to work in the STEM field because there are, again, so many branches and work fields that you can do in STEM. And this program definitely did help me narrow down my decision what I want to do in the future. And it's life-changing. However, the most important thing that happened was you guys gave me this buffet card. Thank you so much. Thank you. Buffet card, smartest decision. Smartest decision. Buffet card. Thank you.
Credit where credit is due. And speaking of,
and for acknowledgments, we would like to thank Dr. Tim Irvin, our mentor, and Mr. Felixson. He was the mentor for the other ICESaT team, Team ICE. Mrs. Baggio, Mrs. Nab, Mrs. Ramirez, and Mr. Johnson, we thank you for all your support and dedication towards this program. We'd like to thank ICESaT Team ICE for helping us with our stuff, and it was a little tough time, but we got over it. Here we are now. The CSR for allowing us to work in their facilities, and the Texas Space Grant Johnson Space Center for allowing us to go in and see the ISS mission control. That was honestly really neat. I definitely go there again any day. And also University of Texas at Austin for putting a roof over our heads, and again for the food. And of course NASA, we'd like to thank NASA because if it wouldn't be for NASA, I don't think we would be standing here right now. So again, we thank everybody, and that's all we have. Questions? Concerns? Suggestions?
What exactly is the Falcon computer? Falcon computer?
Okay, his question was, what is a Falcon computer? The Falcon computer is this dinosaur computer that keeps all the satellite data. It's honestly like your normal desktop tower, except it's specifically used for satellite data. And it keeps it all stored there.
As supercomputers go, it was kind of disappointing to be introduced to it.
It has
say
this
that.
name like Falcon, and we went in and saw it. We're like,
It was
that
all like
one? It's like
remote
on the floor.
access.
Yeah, honestly,
we were told it was being kept in the computer room next door, and
Yeah,
then
honestly-
we finally got to see it, and it's like this tall.
Yeah, honestly, when I first walked in, there's this big tower, and it's like, oh, that's Falcon. And no, it's that small one in the corner.
But it's okay. It did its job well.
It did its job, yeah. Any other questions?
I am not quite sure what you mean by random averaging.
Okay, I'll talk about that. So the averaging we did for the original graphs was, random is not really a good term for computer science, but pseudo-random averaging, where basically it took the data in chunks of 100 and just took all that data and averaged all the values for it in the initial graphs that we did. So I don't know if I can flip all the way back. But in the initial graphs that we constructed where we take a broad graph and then narrow it down, yeah, so these sort of graphs, it takes 100 points, which will be presumably randomly placed around the graphs, but 100 consecutive data points in the txt file, and just squashes them down into one point, so it makes it easier to look at on the graph. And it helps eliminate some of the spread of the data and stuff, so you get a slightly more focused data set. But then some of the other graphs that we used, these ones were, instead of random averaging, we simply looked at all the data points from like a normal graph in one square, and then based on that, we constructed our averages, just averaging the data points in those squares. So if there were, in some of these, yeah, in these sort of things, you get a lot of random outliers up here. And so that's because there was only one data measurement in that square. So it's not a particularly accurate data measurement. But when you get like, I don't know, 10, 20 data measurements in one square inside of here, you start getting really precise data. So we did that mostly to focus on the body of the graph.
Any other questions? Any more questions?